Yes, okay. Hi, everyone. We are here for serverless computing session 2. I'm very excited about the 4 papers. I hope most people had the chance to see the videos. They're very good. And the first one is uh, Vishal Sakar. Vishal works on the foundations of machine learning. He spent 9 wonderful years at UC Berkeley, so it sounds like he misses it. And he was working under Ben Bretchen. Now he works at Amazon on a special project team. So, Vishal, you know the drill. You have 2-3 minutes to remind us about the story.
Yeah. Hi, everyone. My name is Vishal, and today I'd like to talk about a system we built for solving linear algebra programs on serverless infrastructure. So, so I'm primarily a machine learning researcher, and essentially I got into this game because I wanted to solve large linear systems. And so when we built this system, when we built NumPy, and we built it based on 2 key insights. One is that if you look at most complex linear algebra algorithms that are somewhat difficult to parallelize, by complex, I mean something that's not trivial to parallelize, such as matrix multiplication. We're thinking of things like Cholesky decomposition, QR decomposition, singular value decompositions, core subroutines for machine learning tasks. We find that the parallelism of these algorithms through the lifecycle of this algorithm oscillates quite a bit. So what this means is like you'll have a stage where you're using all your possible cores, and then you'll have a serial bottleneck, and so on and so forth. So I have this, the figure I have on the top left is an example of what the parallelism of Cholesky decomposition looks like. So if you have a static allocation of cores, you're going to be wasting those cores in these valleys. The second thing we realize is that you need a large working set to solve a lot of these linear algebra problems. You need the working set is roughly n squared if you have n data points, if you want to solve like a kernel system. And memory is quite expensive, even today in the cloud infrastructure. So if we want to store 1 terabyte on EC2, it costs $7 an hour. But storage itself isn't expensive. We can store 1 terabyte at 4 cents an hour. So, and on S3. Or any type of other object store. And what we found is that we can get insane throughput, read-write throughput to S3. We can do 400 gigabytes out and 300 gigabytes in. And I think these numbers have gone up more recently. And then so putting this together, using the ability to oscillate cores really quickly using existing serverless systems like AWS Lambda and the insane throughput Amazon S3, we built NumPy, which is a system that essentially lets you pose a linear algebra problem in a high-level way, and then have the cloud solve it for you, and then just put the result on S3. So you don't have to manage MPI clusters, and the answer just shows up on S3, and you pay for exactly the cores you use. So essentially the results are. This doesn't come for free. So the results are at the end of the day, you spend less core seconds than you would if you use a standard MPI solver for solving these large linear systems. So if you use ScalaPack, which is a standard battle-tested MPI routine for solving Cholesky, you see that NumPy uses around 30% less core seconds than an MPI solution because it can optimize these valleys. But you do pay a price in the end-to-end completion time. So it doesn't come for free because you have to turn on and off these instances. But at the end of the day, what you're paying for is the total number of core seconds used. So that's roughly all I have. If you see the video, I go into the gory details of how we built the system. And yeah, any questions?
So we have a question on the app, which of course now I had it.
Am I supposed to see? Oh, so it's not something I can see.
No, yeah. So I'll read to you, and then, yeah, and so you're not going to be able to see any of the questions. People can do a little Q&A, and we had a question posted on the system. There was, isn't this approach trading the user's idle time against the provider's idle time. And then if you take the latter into account, are you still saving resources? So maybe, use end-to-end prices indications. The way I understand this question is that, there's no free lunch as you have on your talk. So where's the savings really coming from? Is it
the savings is coming from is the way most of these cloud providers charge you is they charge you by core second. So you don't get charged on end-to-end runtime. So like if I'm like a grad student and I have to solve this linear system for my end application, it doesn't really matter if it takes 5 hours or 4 hours. But the big change is if I'm actually saving 20% of cost, that's a big win for my PI. And that's like roughly why, that's essentially why we built this, because keeping a large cluster alive for a long time is expensive. So we're like essentially not only trading developer hour, and in terms of actual like user hours, there's also no management on my side. It's the standard trade-off you get with most serverless systems, where like you pay a little bit of efficiency, but like now I don't have to think about, oh, how many cores do I need and how much memory do I need to make sure I fit it, my working set fits in memory. The nice part is S3 is like effectively infinite. So like as long as the data set fits on S3, I'm good. Like obviously if you're in the 10, 20 petabytes, then it may not fit on S3, you might get some error, but yeah.
Okay, so we have now more questions here. So Dmitry Ustiagov is, thank you for the call and the talk, and he says, what other types of computation do you envision in FPGAs or embedded processors inside the SSDs? And yeah, so I guess that's it.
Oh, so yeah, I haven't really thought about that. I mean, like in terms of using accelerators, like if there's nothing here preventing me from using better hardware, we could use GPUs or any sort of accelerators and speed up the compute. This isn't along the lines of having FPGAs near the SSDs, because the whole point of the reason the system works is because the compute is disaggregated from the storage. So like that's why we can do this oscillation, because the storage stays fixed. Yeah.
Okay, and Aurelista has a different question. Can you compare the performance of a linear algebra kernel on a single serverless instance versus a virtual machine? So for instance, can you use things like MKL and take advantage of all the fancy SIMD instructions?
Yeah, so
where do you get in core seconds come from?
Yeah, so we are like all the in the individual, so that like I didn't get into the core ED, like this exact, we have a plot of comparing this in the in our main paper, but I think it's like figure 6 or something, but the individual instructions we run on all the machines are optimized MKL kernels. It's just that we can now we are doing hundreds or thousands of these in parallel, whereas on the biggest EC2 machine, which is I think is an X1 32x large, you get maybe 72 of them at once. So it's like 72 is the biggest limit you can get, and there you can only solve your matrix size can't be more than 512K by 512K, and you'll spill out of RAM.
Okay. I don't see another question here in the Q&A now, so let me chat with you. People who come from high performance computing spend their lives optimizing access, so that you put memory, bandwidth, and network, and all of that. And you're saying I can do link pack, which is the dream for HPC. I can do linear algebra, even coming from a disk that can be so far from me, because S3, as you said, it scales, tremendously, which means that your path to the data can get tremendously far. So
yeah, yeah, so
how does this work? What do you have to say to our colleagues on the supercomputing call?
no, like this is only possible because of the work of the because like we're using those algorithms. It's just that those algorithms are so good that we can basically take a factor of two. Essentially we're taking a performance hit. We're taking a pretty big performance hit end to end. But essentially the idea is that if you've ever, as an end user, if I want to set up, I don't want to set up an HPC cluster. Like AWS has a way for me to set up an HPC cluster, but that's so much that's so much work. And here I can get up to 50% of my peak flops just by having this having everything disaggregated. In fact, if you look at these HPC, if you look at the communication, how much communication these HPC libraries are doing, they're so good. They're doing such efficient blocking and caching that they're not even stressing the NIC. The NIC is these machines have a 24 gigabit NIC, and they're pushing maybe 1 or 2 gigabits, whereas all the NICs are pushing at 25 gigabit, are pushing to the limit. So we're just using all the extra hardware that's around more than they are. But if what you care about is end-to-end runtime, then you should use the HPC solution. But this is if I have a million by million linear system that I want to solve, and I'm just some dude from physics, and then this would be easier because I don't have to set up a cluster.
Okay. Now I have 3 more questions, so you can manage your time because we have 4 minutes left.
Yeah.
Simon asks you, what about the actual cost in dollars of running an application, say Chalice, by NumPy compared to the MPI implementation? He's really wondering if it's really cheaper.
I mean, it is going to be cheaper because when you're not running the application, well, it depends on what the application is. If the application is just solving a set of linear systems in a for loop, and they're all really big, then maybe not. But the main thing here is that you're not if you don't need to keep the cluster alive. The nice part about serverless is that it scales to 0. So when you're not using it, you're just if you have some application where for example, sometimes you need to solve a 512K linear system, sometimes you need to solve a 1K linear system, you can now oscillate here. The cost, if you actually use AWS Lambda, Lambda does charge a premium. So in our paper, we do experiments on AWS Lambda, and you can just basically run the exact same thing on EC2 spot instances, but have the same compute model, still be serverless, but mimic serverless on EC2, and then basically you can get that cost back. Amazon charges more for Lambda, and that's Amazon, that's Amazon's prerogative. But at the end of the day, you can always get if you're using less core seconds, then you're using your resources more efficiently, and then you'll get those savings. That's all.
The next question comes from Rodrigo Fonseca. What would you change in AWS, Azure, Google functions to better support your
Yes, it would be nice if we could have it would be nice if I could pay for one is that if S3 doesn't, my understanding is that S3 doesn't have any sort of SLA for whether the request will actually succeed. So a lot of the you lose a lot of time because sometimes when you're making a lot of these requests, they'll fail and you have to do retries, and that becomes quite expensive. And there's no intermediate ground between S3 and it would also be nice if S3 had more atomic operations. They recently introduced some sort of locking mechanism, which could help for some of this stuff. Because some of these applications, I have to do something really hacky to make sure to keep track of state. And the other thing would be the other thing would be if I could get lambdas, if I could get lambdas that are that are slightly beefier, that would also help. Basically, like if I could pay more to co-locate my lambdas, that would also help greatly, because like
One last question, and we have 1 minute, so let's see if we can do it. So Arjit has a follow-up question. So core seconds naturally accounts to core count. It is, you know, dollar core times seconds, you know, cores times seconds.
Yeah.
I'm not, so, you know, we are not sure we understand the parallelism point.
We're not what?
Because the core seconds naturally account for the core count. So what is the parallelism point? Because you're already accounting from it.
So like I think I'm not sure I completely understand the question, but essentially, like, yes, just looking at the core seconds graph doesn't tell you much, because like you could be this could be running for a week on a single machine and it's kind of useless. But like if you look at the core seconds and then look at the end-to-end graph, you're seeing that what you're losing is like something on the order of 20 to 30% in performance. The next is this and you're saving 30%. Like core seconds itself doesn't account for parallelism. It's just saying at the aggregate, like you have to look at both the graphs together. Is basically my answer. Like you have, like, the core seconds in isolation doesn't tell you anything.
Thank you very much, Vaishal. And now we are ready for the next one.
Okay. Can you guys hear me?
Yes. Yes. Hi, Arjun. So Arjun Singh is a PhD student at University of Wisconsin-Madison. He's working with Professor Aditya Kella. He's interested in networking and systems research, with his recent focus on serverless computing, RDMA, and data analytics. So let me put your first slide in, and you're ready.
Yeah, thanks for the introduction. Yeah, so as a part of this project, like the key question which we set out to answer is, how can, say, a cloud provider offer network functions as a service? And here, by network functions, I mean entities like in-network entities such as, say, a firewall or an intrusion detection system, or say a UDP whitelister, which prevents DDoS amplification attacks, right? So the idea was that with more and more applications being offloaded to the cloud, there is this requirement of network functions also to be offered as a service in the cloud, right? And typical requirements of such a service would be that the service should offer an intuitive programming model where the idea would be, given an input packet, what is the processing logic which you would want to go ahead and do. So that's something which the platform or the service needs to expose to the NFV developers. And apart from that, it needs to deliver on the low latency processing requirements of network functions, because they lie in the critical part between the communicating servers. And it needs to scale up and down to meet the incoming traffic demand. And from a user's point of view, it needs to support usage-based billing, so that you're just charged for when your packets are being processed by the system. And if you look at these requirements, and having heard about serverless computing over the last yesterday and today, serverless computing seems to have the right building blocks. If you look at these requirements at a high level, right? It has the intuitive event-driven programming model. It promises to have like the automatic compute elasticity, which seems to have the promise to automatically scale up and down for the incoming traffic demand. And it has usage-based billing. So while it does seem to have the right building blocks, when you look a step closer, you actually see that there are a few fundamental issues with existing serverless platforms today. Like the first problem with existing serverless platforms today is that they offer stateless functions as an abstraction, and network functions are typically stateful. So the only way you would need to, you would persist state across different packets or different function calls would be you writing to a remote store, which could possibly be in memory, say a Redis key value store, but you would still have to incur the overhead of actually writing the state back and then pulling it and making changes. So that has overheads, right, which are not acceptable. So performance is going to be traded off as a result of this stateless function abstraction, which serverless platforms today go after, right? And the second issue, which I want to highlight, is that today in serverless platforms, there is a coupling between the work allocation and the function operation granularity, or the billing granularity. And what I mean by this is that both work allocation as well as function operation or billing happens at the granularity of an incoming event, right? And let's take an example. In our context, an incoming event could be, say, a packet, right? So in that case, you would essentially launch a function for every incoming packet. While this would lead to, say, efficient resource usage because you're launching the function only when a packet arrives, and it leads to ideal billing consequently, it leads to performance overheads because your state needs to be externalized, and also packets are sprayed all over, right? And the same trade-off is trade-off also shows up when you go to the other extreme, where you're launching functions that, say, at the granularity of an incoming flow. So in a nutshell, existing serverless platforms fall short because of these two key attributes, right? So can you go to the next slide, please? Yeah, so with SNF, right, we essentially design a performant and efficient serverless platform, right? It needs to be performant because that's what end users care about, and it needs to be efficient from a serverless provider point of view with respect to the amount of resources which are used to service the incoming workload. So SNF is based on three key ideas. The first one is that given the negative aspects of the coupling between the work allocation and billing granularity, in SNF, we essentially decouple the work allocation and billing granularity. What I mean by this is that functions still continue to operate at the per packet granularity. So you can, it has the intuitive way programmers today think about, but the controller, instead of acting at the per packet granularity, essentially acts at a flowlet granularity, which I'll get to in a short amount of time. And the other key idea is that SNF overcomes the stateless function abstraction by introducing a notion of ephemerally stateful functions. And both of these ideas are realized by leveraging the existence of flowlets in networking traffic today, where flowlets are essentially bursts of packets which come, and then there is a short period of time, and then there is a gap again. And so in SNF, what essentially happens is that packets belonging to the same flowlet or the burst are sent to the same backend container, right? So they can access state which is maintained locally. So you get performance as the state is just local, so it is stateful for the duration of just a flowlet. But apart from that, SNF also uses a proactive state management approach where, say, a packet is a flowlet or a packet is assigned to another function apart from the previous function it was actually assigned to, right? Then we proactively replicate the state, so you no longer have to stall until state is actually pulled. So in a nutshell, we make certain key changes to the serverless platform so that it can support high performant applications like network functions.
Okay, very good. We have a question here already. What happens in cases that the network function affects routing or connectivity? How would this interact with the virtual network infrastructure? For example, right now, cloud providers don't allow IP spoofing.
Yeah, so I think like here, essentially what's going to happen is that such a service would need to actually interact with the virtual networking infrastructure. Like today, the virtual networking infrastructure essentially uses, say, VMs, right, which are managed by, say, a higher level control plane. But here, what we are advocating for is that there is this a serverless platform infrastructure which is available, right, which could prove to be more cost efficient from a serverless provider point of view because it's smaller units of compute, so you can pack them more efficiently. So leveraging that would be useful. So we would have to change the virtual networking infrastructure to actually leverage such a platform.
Okay, we have another question here. So Costas Kafis asks, what happens if a functional worker dies while processing a flowlet? How do you recover? I was very curious about that.
Yeah, that's a good question. So just one clarification, right? So the controller essentially operates at the granularity of flowlets, but it like from a function point of view, the event is still a packet, so it's processing packets, right? So that is one thing which I wanted to clarify. But yeah, fault tolerance is an issue, right? Because now we have stateful applications, and how do you actually ensure state fault tolerance, right? So I didn't go into the details here, but in the paper we have like a lightweight fault tolerance mechanism where the high level idea is that we replicate the state before actually letting the packet out of our system, so that in case of a function failure, we can read it from there and continue processing it.
Okay. Okay, let me see if we got more questions here. So while we don't have more, let me ask you, this is probably not totally particular to your exploration of serverless, but what I worry is on problem determination. So if I'm responsible for some network system, when I was managing it through network functions deployed on VMs and everything, I probably had a way of understanding because it was not varying, so quickly. I could reason more about what was going on in the system. Now, you have the great characteristic that you pop up things for flows and come, so really scale. But what about problem determination? Or you talked about failure, but what if you present, for example, we start to see a cascade of failures? Is it harder to reason about the system than it was on traditional VM deployed environments?
Yeah, so I think so one thing with serverless platforms today, right? Like the thing is the ability to trace and debug them and actually observe them is sort of limited, and also it is more difficult than say how we would possibly use traditional VMs, because there's more rapid reassignment of processing. So there is a lot of movement going on, right? So from that aspect, I think it does become a bit more challenging to actually say monitor such a system. But I think like in SNF, what we do is we essentially have the controller, which essentially maintains like persistent connections with the backend containers. So if it doesn't hear back from them, then it knows that something's wrong there. So it would need to take a failure recovery action. So like fault tolerance would need to be built in that aspect.
Okay. How do you deal with cold starters and more generally with the latest requirements of processing flowlets, which seems much faster than any current framework can handle?
Yeah, so that's a good question, right? So currently in SNF, like the scaling algorithm which we have with respect to the serverless infrastructure is that if say 90% of the existing containers which are launched are full, then essentially we would are utilized. Then we essentially launch one more container, right? And that seemed to work in the workload traces which we were targeting for. But yeah, cold start I think is a very important problem, because we can suddenly have bursts of packets which are coming in and we don't have warm containers in the backend, right? So how do we deal with that? So I think that is an important problem which we have to look into, and that's something which we are also actively looking at, apart from all the other efforts in the community.
Okay, I have here a question. Does the framework depend on the sandbox runtime technology? Would this work well if the sandbox is a VM?
So in SNF, like the mechanisms and the ideas which we have isn't particularly tied to any particular sandbox technology, like say a virtual machine or a container or a hybrid between the two, right? That's something which SNF doesn't really look at. But I think what would actually determine the backend sandbox technology would be taking into account the security requirements. And I think we as a community should pick something which does not sacrifice security for, say, some performance improvement.
Okay. In the line of the cold start, I think a good question here that arrived is, could you talk a little about how the end-to-end latency is affected by functional invocation latency? Would something like that work in a cloud provider serverless offering?
Yes. So the thing is that the end-to-end latency, like say in case of such applications where latency is so critical, right? The cold start will actually dominate a lot because it takes, like Firecracker, for instance, today takes 125 milliseconds, right? So that would actually lead to a latency, right? But I think the future would be that if we want to cater to such high performant workloads, then the sandbox management needs to be more proactive and needs to essentially take that into account and then appropriately manage the backend infrastructure.
Okay, I think we are getting at the end. We don't have more questions. Thank you so much for the presentation. I think that even the short one was very effective in providing a view of your work. So we will get ready for our next one, which is now Ali Tariq. Hi, Ali. So Ali is a third-year PhD student in computer science at the University of Colorado Boulder. We see the beautiful background that he has on his Zoom. He works mainly on serverless cloud architecture. His focus has been on to make emerging cloud applications easier to manage, and he is looking for internship positions for summer 2021. So our industry attendees, pay attention.
Thank you for the introduction.
You can start and you can tell me when to change to the next slide.
Sure. Hello everyone, I'm Ali Tariq from University of Colorado Boulder, and today I'm going to briefly summarize our latest work, Sequoia, enabling quality of service in serverless computing. Serverless is the new event-driven paradigm that allows us to use small, short-lived functions where the developers only need to worry about the application logic. Runtime environment, package dependency, and function scaling are all taken care of by the platform itself. Now, this provides a more productive environment for the application developers to focus more on the applications. Serverless architectures provide seamless scalability to the incoming demand, which means the developer no longer has to do any kind of over-provisioning. Fast service setup and fine-grained billing are among the major reasons why we see today serverless is getting exceedingly popular. But even with all those benefits, there are certain limitations in today's ecosystem. Serverless has shown great support for a diverse variety of workloads, starting from chatbots to machine learning jobs. Now, this kind of flexibility gives rise to more complex applications. These applications overburden the application developer to provide the necessary SLAs, such as reliability, deadline completions, and other workload management on the application layer itself, which goes against the basic premise of serverless computing. So due to the very limited quality of service support, our work aims to provide the much required QoS framework for the serverless applications. In our work, we actually provide a detailed measurement study across 5 major serverless providers that identifies several limitations. We then propose a new lightweight QoS scheduler that can help address the existing challenges. We evaluate the proposed design on both artificial and real-world workloads. Our source code has already been open source. Can we move to the next slide, please? So today we'll briefly touch upon 2 major sections from our work. We start with a measurement study to understand more about the existing infrastructure. On our methodology, we use function chains with fixed length functions. For the functions, we use function wrappers with the logging server to keep track of the function invocation progress in real time. Our study showed various issues across all serverless platforms, such as concurrency limits, mid-chain drops, and undocumented prioritization. In addition to the existing issues, we see very limited quality of service support other than the basic primitives provided by the orchestration frameworks. Now, these basic primitives are nowhere near what we need for the existing requirements of quality of service for the serverless domain, which is why we provide a new QoS scheduler, Sequoia, that makes use of flexible policy framework, which allows the users to build their own custom scheduling policies. In our evaluation, we show how the users can implement shortest remaining job first and get up to 25 times runtime performance benefit on real-world applications. We further see how it can also provide more than 6 times reduction in the queuing times of the functions for the more latency-sensitive applications. Again, with Sequoia using fair chain scheduling, we see how the Sequoia is able to achieve near optimal fairness between 2 real-world workloads. So in summary, Sequoia provides various performance benefits along with the much required quality of service support that is required by the existing infrastructure. that can help address the existing challenges we are facing today. Thank you. I'll be happy to take the questions now.
Thank you, thank you. And I'm sure more questions will come, but we have here, what quality of service strategy do you think a serverless storage system like Pocket should implement?
Yes, so regarding that, so again, I did not get a chance to go into the details of the Pocket system, but from the brief overview, I can understand it's a high performance storage system for serverless workloads. So in that case, a more resource aware scheduling policy would be more appropriate in that scenario, because quality of service is a very vague term. It can changes, it can be subjective to the existing scenario. So in this particular case, you can actually have data locality or hot caches that can actually help you if only if you have some resource aware scheduling in place for the Pocket system.
Okay. Another one, after Sequoia schedules a function, the function as a service platform has to route the request to a worker node. Is there any info that Sequoia could add to the request to help the platform with its routing decisions?
So currently, with the current implementation, we have actually implemented it as a proxy design. So it is going to sit between the user and the fast service provider. So whatever the user wants as an extra information for the fast provider, Sequoia can actually take that extra information in and make policy informants based on the extra information. But unfortunately, today, the fast providers do not provide us with an interface that we can use to add this information for the fast invocations. So in future, if any fast provider does come up with such an API, then sure, we can actually add that. So the existing implementation is actually flexible enough. So Sequoia can actually interact with any new interface the fast provides us. We can definitely opt with that options as well.
Okay. And I will borrow a question that Rodrigo Fonseca asked before that follows up what you're saying. What is your wish list to the cloud providers working on that infrastructure? What do you think you could do that would make you managing your chains and the whole approach to work better?
Again, I think it can be started from the previous question. So currently we don't have any control. So the Square is actually implemented in a way that even though the users don't have control or influence on the fast providers infrastructure, you can still do so much. But if you do get that control, that means you can further go down to the gory details. Like if you have this much invocations, let me just invoke only this set of containers, which means you are no longer just thinking about the quality of service, you are also managing the workload in a way that's like very strictly enforced. That's again, it's up to us and it's up to the fast providers how much support they want to provide to the users.
So we have a question here. Brian Kim is saying, interesting work. What was the most unexpected result, surprising result from the measurement study?
Okay, so the most surprising work was actually the concurrency collapse we saw for the fan and workloads. So that's a special type of workload where one function is actually spawning a number of new functions. So for that particular kind of function, we see a very imminent collapse just after you actually hit the concurrency limit, which means you would see the whole concurrency thread pool is actually going idle, where you're very slowly recovering the lost concurrency pool, which is very weird. And again, because the whole AWS is a black box for us, it was very hard to actually debug that. How is it happening? It shouldn't be happening. So that was a really surprising result for us.
It sounds like. And how do you define fairness in a multi-tenant setting? Are you advocating, in a multi-tenant setting, are you advocating that Sequoia sits before the function as a service platform as organized? How would you guarantee that fairness?
So in the multi-tenant setting, so the current implementation is targeted at individual users. So the users will be actually using Sequoia to manage their workloads. But if you are talking about the multi-tenants, then you are actually talking from the perspective of service providers. In that case, service provider is going to have the holistic overview about individual usage of each of the tenants. In that case, it won't be the exact implementation. It would be more scalable with like distributed setup. But even in that case, the the service provider will still have the same overview on the resource usage. So it won't be sitting in between. It would be integrated with the infrastructure of the FAS provider.
And if the provider were to provide scheduling support for serverless functions, what performance metrics, QoS, information do you think the user should be providing and why? So that's the only issue.
So the users only need to define what they want out of that application they have implemented. So if they have like multiple applications, they have to decide whether this particular application is like latency sensitive, or part of this application is like just the archiving or logging functions that are like keeping track of how the execution ran. So they only need to provide what they want out of this application. And they can define that via various scheduling policies, the way we have actually shown in the paper. So the user actually can define, if they have two applications, what if they want equal allocation for both of them? Now it's again a question, if the first application is like really small running function and the other one is a really long running function, do you still want fairness or not? It's up to the user, because he's the one who's actually paying for this stuff.
Okay. And could such a QoS schedule be built on top of existing frameworks, even their inefficiencies and unpredictability?
Definitely. So that is actually one of the promising direction we are pursuing right now. So what we wanted for this particular work is we wanted to measure the existing quality of service across different platforms. So you can't do that if you are sitting on top of one of the platforms. So if you want to do that, that's what we are actually hoping now. What if we could integrate the existing Square framework with the OpenWhisk or any other open source framework, and see how better we can actually do with this, because you are going to have much more flexibility than what you have right now.
And Vivek Bazi is asking, you mentioned weighted priorities as a possible scheduling mechanism in the paper. Could you elaborate on that? Do you allocate different proportions of concurrence to functions? And if so, on what basis?
Yes, so we actually did implement a built-in policy regarding the scheduling, where you can actually prioritize different function chains or different functions within a single function chain. So the basis is again the same. So let me give you an example. You have a really long running function. You have 5 functions in a linear setup. So the first 4 functions are actually application that are doing something, but the 6th one is just a logging function that actually saves the logs from first 4 functions into some data store. So this function is low priority. So what you want, you can't really have this function actually affect the performance of the first 4. So you can assign the priorities based on something like this. So only run this last function when you have the resources or when you don't have enough incoming demand. But if you have the incoming demand, you should actually prioritize the actual function that is going to help the users, your customer base, or whatever service you are actually providing.
Okay, let me see if any more questions arrive in my systems. Okay, since we have a minute or so, can you tell us about what is the future work that you discuss in the
Yeah, so like I said,
next?
So the next step is actually to integrate it with one of the existing frameworks. The preferred choice is OpenWhisk because we have been testing a lot with it. We are pretty much comfortable with the existing framework. So that's the first step. So that's where we are going to start. We just wanted to show how if you have that flexibility to actually influence the actual fast infrastructure, you can go beyond what you are actually looking in the paper. So in the paper, you are very limited. You can't really control that thing, but then you can actually go beyond this. So that's the next step we are going to take.
Okay, very good. Thank you so much. This was really informative. And let's now go to our fourth and last paper in this session. So Wen, hi Wen.
Hi.
So Wen's a fourth-year graduate student at UC Berkeley. He's advised by Scott Schenker, and he's doing research in computer systems. So I'm going to go to your paper, Kappa, Programming Framework for Serverless Computing, and when you need me to change, I will. So it's time, you can start. Thank you.
Yeah, thank you. Thank you for the introduction. And hello, everyone. My name is Wen. I'm excited to present Kappa, a programming framework for serverless computing. So as we heard in previous talks, serverless computing, although originally designed for event handling, has been increasingly adopted for general workloads due to its elasticity and ease of use. For example, prior systems have used serverless in diverse application domains, such as video encoding and numerical computation, essentially using these Lambda functions as compute cores. While many of these systems are specific to their use cases, our goal here is to build a general framework that enables even more types of applications on serverless while maintaining the advantages of the platform, thus making it a scalable substrate for general purpose computation. However, using serverless for general purpose computation is difficult for two reasons. First, a general workload can be long-running, but serverless Lambda functions are time-bounded, for example, by 15 minutes on AWS Lambda. The programmers would have to then predict how long the piece of code takes to run, and then manually partition their code to fit within the time limit. Second, while general workloads exhibit diverse concurrency patterns like fork join and message passing, existing serverless offerings lack the concurrency primitives that would be needed to allow synchronization and communication between the Lambda functions. Although there are serverless frameworks that allow that offer these concurrency primitives, they require expressing the applications in an unfamiliar form, say as a state machine, which can be burdensome to programmers. Next slide, please. Cool, thank you. And so to tackle these challenges, we introduced Kappa, a programming framework for general purpose serverless computing. Kappa provides three main features. First, to enable long-running computation on time-bounded Lambda functions, Kappa checkpoints program state occasionally so that when the Lambda times out, the computation can be resumed on a fresh Lambda function from the previous checkpoint. Our checkpointing mechanism operates at the language level and is based on continuations. Second, to enable parallel programming on serverless, Kappa provides a concurrency API that enables the coordination and synchronization between Lambdas. Our API provides standard constructs such as task spawns, futures, and message passing, and is designed to be familiar to programmers. A consequence, however, is that Lambdas that invoke this concurrency API can now exhibit non-determinism and side effects, which complicates checkpoint rollback in face of Lambda timeouts. Thus, the third feature provided by Kappa is fault tolerance in this respect, ensuring that in face of checkpoint rollbacks after Lambda timeout, execution never diverges due to non-determinism, and side effects are never duplicated. And while providing these features, Kappa requires no modifications to the serverless platform, and it can execute on today's existing serverless offerings. Using the rich features provided by Kappa, we have built different types of serverless applications, including big data queries, streaming analytics, and concurrent web crawling. we believe that Kappa opens up the possibility for many more applications to take advantage of the elasticity and convenience of serverless. And Kappa is open source, and you can find its source and documentation at kappa.cs.berkeley.edu. And thank you, and I'm happy to take questions.
Sorry, I was on mute. Yeah. Okay, we have a few questions. I'm going to do first. What is the advantage of using serverless functions rather than VMs for applications that run longer than 15 minutes?
So that's a great question. So we believe that doing long-running computations on serverless can be beneficial to both the cloud tenant and the cloud providers. So from the tenant side, you don't have to, well, if you use serverless functions, you don't have to provision VMs or scale up and down or install operating system, etc. So that's removing the burden from the tenant. And from the serverless provider's perspective, by limiting the duration of Lambda functions to a short amount, say like 5 or 15 minutes, this allows them to more flexibly allocate resources and move jobs around. For example, if the cloud provider wants to move a VM that is currently running, it's not trivial because you have to do migration, etc. But with Lambda functions, you can just wait for 5 or 15 minutes and kill it. And so yeah, our goal here is to retain this benefit for both the tenant and the cloud provider while enabling more applications.
We have now many questions, and I'll get them out of the order because I think that I could ask one that is related. So Shivaran Venkataraman says, nice talk. What are some applications that don't work well in the Kappa model?
Yeah, that's a great question. So currently, so as I said, we have a concurrency API that allows a message passing, and we need to provide fault tolerance for it because if we roll back computation, we don't want to send the message again, right? So to do this, we take a checkpoint for every message we pass. And so in the current implementation, application would not perform very well if there is a lot of message passing going on. For example, you can imagine a graph algorithm, let's say, doing a distributed DFS or something, where the Lambda functions talk to each other to exchange information about like nodes on the graph. That kind of workload Kappa doesn't support very well currently, I think. So it can be future work to make it go faster.
Okay. Eric Rosner is asking, first he says cool work, and then he asked, might this approach make debugging more difficult? Do you anticipate any unintentional or new bugs that the system may introduce?
That's a great question. So actually, I think the opposite is the case. I think using checkpoints can simplify debugging, because I think one issue with traditional serverless computing is that if something goes wrong on the Lambda function, the Lambda function gets killed immediately, and then you don't have any insight into what's gone wrong. But with something like Kappa, what you can do is you can download the checkpoint from when it went, right before it went wrong, and then execute it locally on the VM, for example, and see what happens, say like what crashed. We don't have this implemented in Kappa yet, but I have done this manually for one of our applications, and it allowed me to debug a problem that occurred like on Lambdas that I wouldn't have otherwise.
Yeah, no, yeah, we could take this further because supposedly, with the distributed system, checkpointing can become complicated. The high performance computing people tell us, right? But I think I get it. Christina Dimitriou is asking, do all I/O and data exchanges go through the centralized coordinator? If so, does it become the bottleneck? And then how do you address this?
Yeah, that's a great question. So in Kappa, whenever a task takes a checkpoint or incurs or does a concurrency operation, it sends an RPC to the coordinator. So all like control messages, let's say, do go through the coordinator. Although if you, let's say, like send a message to another Lambda function and the message is big, then we allow you to store the message itself on like S3 or Redis, and then only passing a handle to that message. So currently the coordinator is centralized, but we have shown that, for example, function, each taking a checkpoint, like every 100, we can still handle that. So even if we have 1,000 Lambda functions, the checkpoint latency does not decrease. But we can imagine that, yeah, this is becoming a problem if we have like 10,000 or 100,000 Lambda functions. So it is future work to consider how to distribute the coordinator to address this.
Okay, and do you support the stateful serverless applications? Meaning, do you store the intermediate results somewhere between continuous operations?
I see. So what Kappa does allow, for example, is say you can launch a bunch of tasks and then you pass the futures of those tasks to a subsequent batch of tasks so that the later tasks can use the results of previous tasks. I'm not sure if that's what you meant, but we do allow that.
Yeah. What exactly, oh, I'm sorry, where exactly is the checkpoint state stored? How is this different from what happens in current platforms where state is recovered from remote storage?
So our checkpoints are stored in, so we currently support either Amazon S3 or a Redis cluster. So not on the Lambda function itself because it dies. With respect to how it differs from current, what is the current systems that we recover from remote storage?
Yeah.
I'm not sure what systems are being referred to here because I believe that this is not done for serverless. So in traditional serverless computing, you don't recover state from remote storage. Right? So like what happens is an event comes in and the Lambda gets spun up and does some computation and then dies. So I think we're like introducing this checkpointing and recovery mechanism into serverless.
Okay. What is the minimal granularity that you support for checkpointing or continuation? Does the state gets replicated based on future invocation?
The minimum granularity for checkpointing. I'm not exactly sure what this means. So
think about the continuation. If how much you're storing does. I'm reading to the question. The way I understood is that if you know about what the continuation is going to do, maybe you will replicate state in a different way, on future invocations.
So for example, one thing that we do is if you say you launch 1,000 Lambda functions, so say you want to like do a map operation on Lambda functions, so you launch 1,000 of them, each doing the same computation but on different like arguments. Here, Kappa has an optimization that allows you to take only one like initial checkpoint for these 1,000 subtasks and spawn like 1,000 Lambda functions to load from this one checkpoint and then but apply different arguments. And in this case, we do allow replicating this checkpoint to like multiple Redis instances, for example, for load balancing.
And Leshu got us a clarification. He meant if the invocation is changed, so it's an event that is recurring.
I see. So I think we're talking about different use cases here. So Kappa, our mental model for the application we support in Kappa is it's like one big computation, say like a SQL query or a matrix multiplication. You start and then you launch a bunch of Lambdas, do a bunch of computation, and then you end with a result, and the workload is done. I think the question is referring to like event handling, where the event is occurring. So we don't have that right now. Yeah, so it's not something that Kappa supports at the moment, but yeah, we can totally think about it.
Have you considered compiling Kappa programs to run on job scoped VMs?
Yeah, so if we can treat the VMs as like each VM as a Lambda function, then we can totally do that. And if they're long running, then we don't need to, well, if we assume they don't fail, then we don't need to take checkpoints anymore. So that's true, yeah. But we do believe that this takes away the advantage of serverless from both the tenant and the provider. So, but yeah, it's definitely doable.
And have you thought of ways to make the scheduler serverless? what kind of service or infrastructure would you like cloud providers to offer to make that happen?
That's a great question. So basically, can we implement the scheduler and the coordinator on Lambdas? Right. So I believe it is possible, because if we look at what the scheduler is doing, right, it handles RPCs from tasks when they like take checkpoint and like perform synchronization. So the scheduler in itself is a like large event handler. So I guess it is possible to like store the scheduler state in a store like Redis and then do the computation on serverless functions themselves. So it'll make it even more serverless. Yeah.
Okay, very good. I think we exhausted the questions and we are in our last minute of the hour. So I'd like to take the opportunity to congratulate all the authors, the presenters and the authors. I saw many of the authors in the audience and I thought about bringing them, but in the end, I was not able to do that and get distracted from the presentation. But anyway, so thank you very much. And thank for the participants with the very insightful questions. And Christina or Rodrigo Fonseca, Christina Delimitru, if you are and want to tell us something, otherwise we're going to close the session.
All right, thanks a lot, Dilma, and thanks a lot to all the presenters. So the Gather platform will be open for the next half or 1 hour. So if you have any follow-up questions for the authors, you can head over there. Otherwise, the official program starts at 9:45 Eastern tomorrow. Thanks, everyone.
Bye, everyone.